Okay, welcome guys. So yeah, now we are going to discuss um, one of the special concept of function, which is that of the inverse function. You see, so this discussion is going to be brief. That is, we're not gonna learn about how to find the inverse function because we have already done that in the elementary discussion of functions that we once did before, so you can check the previous videos to see how to find the inverse function. But now we want just some things that we'll need for our abstract notions. So let's talk about inverse function. So what is an inverse function? You see, so given a function f that maps some set A to some set B, the inverse function of f is another function B which maps B to A such that the following is true. You see that? That is, if you take f of g, it's the same thing as saying g of f, and this gives us the identity. Okay, sorry. I was supposed to actually define it this way. You see? So the inverse function of some function f is another function which is g which maps b to a. So it takes the range and maps it to the domain, and it has the following properties. So it has the following properties. A. So when you take g and compose it with a, then this is just the same thing as 1a. Then b, if you take f or g, this gives us 1b, like that. You see? So that's what we mean when we talk about an inverse function, that it is a function which satisfies this condition. So if you compose it from the left, you see that you get 1a. When you compose from the right, you get 1b, like that. So that's exactly what we mean when we say a function is an inverse function, you see? And only uh, and only bijective functions you have inverses. You see, so not every function is an inverse. It is only bijective functions that have inverses. You see, so many other functions, they do not actually have this kind of thing. It's only bijective functions which have inverses. So it's good to always know that. You see. So also, we're not going to actually do examples. We just want to state the definitions that we need, so that when it comes to abstraction, we always know how to deal with all this stuff. So the next thing that we're going to do now is we're going to look at one of the important theorems that you should know when it comes to inverses. You see that? So the inverse of any bijective function f from A to B is unique. You see that? So the inverse of any function is unique. So those are things that you should know. That if you take any function which is bijective, the inverse of that function is always unique. So that's one thing that you have to know. But now, how can we prove this? How can we prove that the inverse of any bijective function is unique? So what we're going to do is we'll say, suppose f from A to B is a bijective function. Then I will say, suppose also that function g, which maps to B from A, and another one h, which also maps to B to A, are inverse functions. So are inverse functions of f. So we want to prove uniqueness. Uniqueness means there is only one of such kind, as now we've assumed that there are two of such kind. So we want to show that actually they can't be such. So one way to show that is either to show that these two actually, when they both exist, they have to be the same thing. You see? So that's what we're going to do then. So now we've assumed two inverses of the same function f. And let's see if we have something like that, what happens. So now, what do we know? So now, let's take one of these inverses, g. So what is g? G, by definition, we know something about g. We know that, what do we call this? We know that if I have g, I can take 1b and compose it with g. It's still the same thing as g. You see that? So we know that taking the inverse of the set b and composing it with g from the left never changes anything, which means that the result is true. You see that? But now, according to the definition that we stated of a function, what do we see? We see that if you take a function and you compose it with its inverse, you always get 1b, you see. So that's one thing that we see there. So let me see that actually I did the correct thing here. So g takes a, so g, so let me study this composition and see where exactly its goal is taking me from, so that I can see that these two are equivalent. So g will take us from B and then to A, but so this is not a true statement. It's supposed to be 1A actually, not that. You see. So those are things that we should pay attention to. So it means actually what we are supposed to do is to say 1A composed with G is equal to that. So always make sure that you wrote the correct thing. And how you check, like how I checked is, I know that G will always take me from B to A. So the next function that must continue must always be able to take me from here going to the other side, like that. Oh, so it was okay. So B will take me from there. So B will take us to A, and then A will take us to B, like that. So we know that this is actually 1B. So which means it's supposed to be 1B actually that works. So I think I'm not sure what I'm messing up here, but it's supposed to be 1B that is supposed to work. So since it's 1B that is supposed to work, then let's try and replace it. So I say this is equal to 1p. So is that a valid composition? So let's check if it's a valid composition. So I know that G will take us from A, from B to A. No, so it's 1A. Because the function that is on the far left must be able to continue from where the previous one left off. So yes, it's 1A. Yeah, why am I messing up? So it's 1A. Because yeah. G will take us and learns that A, this has to continue from A and gives us the other thing. So now we are here. But what do you know about 1A by definition? So 1A by definition, we can see that it is GOF, which means actually it can be written as HOF, then OG, like that. Because remember, H is another inverse of this function. So H is another inverse of this function, like that. Then since we know that H is another inverse of this function, what follows next? So we know that the composition of three things is associative, which means I can remove the brackets and place them wherever I want. So I can remove them around H and F and actually place them around F and G, like that. So inside now I have the composition of F and G. But what will that give me? So if I compose F and G, you will see that actually I will get HO1B. You see that? So I'll get HO1B. But we know that any function composed with the identity is just itself. So I get H. So therefore, what do we see? So therefore, what we have just proved here is that G and H are just one and the same function. So thus, it follows that the inverse is unique. So yeah, that's how the proof goes. So yeah, that's it. So thank you guys for watching. So I'll see you in the next discussion. Bye.